Welcome to RSCH503, Research Methods and Biostatistics, a 3-credit graduate course offered by Drexel University College of Nursing and Health Professions. Scientific research is the systematic study of the relationships between and among variables. Bivariate correlational analysis measures the magnitude of linear relationship between two variables and is conducted on data collected from a single sample. Correlational techniques are available on all 4 levels of data: nominal data, in which the phi, contingency coefficient, and others are used; ordinal data, using the Spearman rank order correlation coefficient and others; and lastly, interval and ratio levels, which utilizes the Pearson product moment correlation coefficient. Correlational analysis tells us both about the nature and the direction of the relationship, that is it positive or negative, and the magnitude or strength of the relationship. A correlation coefficient is a single number that indicates the strength of association between two variables x and y. Such coefficients reflect the degree to which mutual relations between x and y resemble a straight line. Pearson's R is the most commonly used correlation coefficient. Again, it is used with continuous variables. Correlated variables are those that tend to vary together. That is, when one is larger, the other tends to be systematically either larger or smaller, termed concomitant variation. There are 2 types of correlation: positive correlation and negative correlation. When two variables are perfectly positively correlated, a direct relationship exists such that a higher score on one variable is always associated with a higher score on the other variable. This perfect positive correlation will have a value of +1. When two variables are perfectly negatively correlated, an inverse relationship exists such that a higher score on one variable is always associated with a lower score on the other. This perfect negative correlation will have a value of -1. When there is no relationship between two variables, they are said to be uncorrelated and the value is 0. Scatter plots or scatter diagrams assist in illustrating relationships between variables. In this slide, the relationship between speed, x, and distance, y, is illustrated in a scatter diagram. The r value obtained is indicative of the slope of the line, called a regression line, that can be drawn through a standard scatter plot of the values of 2 paired variables. Causation implies correlation, or covariation, but finding that x and y are correlated does not necessarily imply causation. However, covariation is essential evidence for making causal inferences. The assumption of linearity underlies the mathematics of the Pearson correlation coefficient. This slide illustrates the scatter plot between x, hours studied, and y, grade. The Pearson's R was R equals 0.89. This is a positive correlation coefficient, with the R of 0.89 indicative of the slope of the regression line that can be drawn through the scatter plot of the 2 variables. This slide illustrates the scatter plot between x, scores on the global assessment of functioning, that is, a test to rate subjectively the social, occupational, and psychological functioning of adults, and y, scores on the forensic assessment of symptoms test, a test for malingered psychiatric illness. This plot reveals a negative correlation coefficient, indicating that the higher GAF scores are associated with lower FAST scores and vice versa. This slide illustrates a scattergram of uncorrelated variables. In this case, the variables are the height and raw reading scores of both 6 and 10-year-old children. This scattergram illustrates uncorrelated variables. This slide illustrates a variety of scattergrams of correlation coefficients. Pearson R values between variables, from R values of 0.00 to 0.99. It is important to reiterate the difference between a continuous variable and a discrete variable. A continuous variable is one that can take on an infinite value between its minimum value and its maximum value. A variable that cannot do this is termed a discrete variable. Pearson's R can only be computed between continuous variables. Several factors may influence the value of Pearson's R correlation coefficient. First, the magnitude of the R is unaffected by adding a constant to either or both sides of the variables. Second, the magnitude of the R is a function of the variability of the measures. The larger the heterogeneity of the variables, the larger the R value. And lastly, the correlation assumes a linear relationship between the two variables. A curvilinear relationship will invalidate the use of the R coefficient. This is noted simply by inspecting the scattergram. The correlation or relationship between anxiety and performance, for example, is a curvilinear one. At low to moderate anxiety, a subject's performance increases. However, as anxiety becomes increasingly high, performance decreases. Since the relationship is not a linear one, the degree of relationship between these two variables would be grossly underestimated by the calculation of Pearson's R. How does a researcher interpret Pearson's R? 3 points to keep in mind. 1. R is a function of sample size. Large correlations achieved by small samples may be completely meaningless. 2. The degree of relationship is independent of the sign of the R, whether it is a positive or negative R. And 3. R is an index of the concomitant variation of two variables, but it indicates nothing about the magnitude of the variables. Possibly the most valid and useful interpretation of the correlation coefficient, that is, R, is achieved by squaring it. It is possible to demonstrate that R squared is the ratio of two variances. The denominator of this ratio is the total variance of one of the variables, and the numerator is that part of this variance that can be predicted from or attributed to the other variable. Thus, R squared is that proportion of the variance of one measure that is accounted for by the other measure. R squared is called the coefficient of determination. Again, the coefficient of determination, or R squared, is that portion of the variance of a variable that can be predicted by or determined by another variable. The coefficient of non-determination, or 1 minus R squared, is that proportion of the variance that cannot be predicted by or determined by the other variable. A serious mistake that can be made by an investigator is to interpret a statistically significant correlation as evidence of a cause and effect relationship, or simply a causal relationship. The Spearman rank correlation coefficient is an adaptation of the Pearson's R for use with ordinal data. An example of the Spearman-Rowe coefficient is the correlation between the rankings of the top 25 college basketball teams by sports writers with the rankings of the same teams by college coaches. Since this coefficient is used with ordinal data, it is a non-parametric statistic. Factor analysis and principal components analysis are statistical techniques designed to examine interrelationships among large numbers of variables, to reduce them to a smaller set of variables, and to identify clusters of variables that are most closely linked together. Such clusters are called factors. Principal components analysis is used to assist with validity investigations of a new instrument or scale, particularly subjective assessments or instruments. The number of population subgroups, that is, independent variables, is dealt with simultaneously in the analysis. The results of principal components analysis assist the investigator to understand which questions in an instrument are redundant, which questions represent subsets of variables, and which items stand alone and reflect unique concepts. Again, these techniques are commonly employed in instrument development. This slide illustrates the process of factor analysis. 4 items are grouped into a factor called working memory capacity, reflecting short-term memory and digits forward. The remaining 4 items, reflecting executive control and digits backward, are grouped into another factor of working memory capacity. In summary, factor analysis is a statistical method used to describe variability among observed, correlated variables in terms of a potentially lower number of unobserved variables called factors. This presentation was prepared for graduate nursing students at Drexel University College of Nursing and Health Professions. The primary book used in this research course is The Practice of Nursing Research, Appraisal, Synthesis, and Generation of Evidence, 2017 edition, by Jennifer R. Gray, Susan K. Grove, and Suzanne Sutherland. This book is published by Elsevier Saunders, St. Louis, Missouri.